All right, so in this lecture I would like to talk a little bit about how you actually, let's say in deal.II or in any advanced finite element code, you represent the data structures or the objects that we have talked about. So we talked about, for example, the triangulation class or the deal.f handler class, and we talked about matrices, vectors, and so on and so forth. In most of these tutorial programs, the data structures that underlie these classes are very much black box. You use them through member functions. You almost never access directly from user programs individual parts of the data. So you will have seen, for example, that we're very careful almost never to expose member variables. All the interfaces that you always work with is member functions, but never do you actually use member variables of these classes. And there's a good reason for this that I'll come back to in a minute. But so what I would like to do is essentially digress a little bit and give you a little bit of an idea of how these data structures are chosen and how today we represent, let's say, the modern finite element concepts in code, even though you will never have to do this yourself when you build software on deal.II. It is more of, let's say, a little piece of background that I would like to introduce you. So this is lecture 22, and what I would like to do, as I say, is talk about some design considerations for data structures. And I would like to start essentially in the same order in which we have walked through the building blocks of a finite element code. So the first one that I would like to look at is how do we represent triangulations in today's codes. So I think all of us have, of course, written a simple finite element code once for the first time, let's say as an exercise in one of the classes that we take in college. And I would venture to guess that for most of us, it has probably looked roughly like this. This is pseudocode. If you can read C or C++, you understand what I mean by this. This is not supposed to compile this way. So essentially, what we do, let's say we really want to store a triangulation in the sense that it has triangles. So it's only in 2D here. So we create, for example, a structure that we call vertex. And of course, it has two components, the x and y component of a vertex. And so it's an array of elements double of length 2, and we call this array coordinates. And then we can represent our mesh as a collection of triangles. We call them cells, and each cell is characterized by the 3 vertices that it is adjacent to. So we could, of course, store again in the cell the coordinates of these vertices, but what we really much rather do is just store the number of the vertex. So each cell stores the 3 indices of the vertices that bound it, and the indices are, for example, integers. In deal.II, we would actually represent it as an unsigned integer because the vertices will be stored in an array, and so the first one would have index 0, the second one would have index 1, and so on and so forth. There can never be a negative value, so we would always use an unsigned integer for this. But this is just for illustration here. And then, in essence, a triangulation would just consist of the following. It would consist of an array of as yet unspecified length of vertices. Okay, so as I say, this is just pseudocode. In C, this wouldn't immediately compile. But let's say it is an array of as yet unspecified length that stores the coordinates of all of these vertices. And then there is an array of also as yet unspecified length of these objects cell that represent the indices of the vertices that bound each one of these cells. So I'm introducing this to you because I want to make the point that this is not good design for a number of reasons. So if we write, if in deal.II the triangulation class really was represented like this, it would not be, let's say, an extensible design that would have carried us for 15 years. So among the reasons why this is not a particularly good design is something that we call lack of encapsulation. So when you learn about object-oriented programming, one of the things that you learn very quickly is that you cannot expose the details of a data structure to a user. Let me illustrate this here in the following way. So if I was to use this triangulation class in my own user programs, then I would access these cells by accessing the member variable cells of this triangulation object. And if I wanted to get at the coordinates of the vertices of this cell, then I would have to access the corresponding vertices array of the triangulation. So in other words, I would have to litter my code with places where I directly access these member variable cells and vertices, and where I use knowledge of how exactly the data is stored. So for example, I would have to assume that the elements of this vertex indices array here in each one of these cells are actually indices, or let's say offsets, into this vertices array here. And so what I do is implicitly I use a lot of knowledge about how the data is actually stored in my code. And that's fine if my code has, let's say, 1,000 lines of code. But in reality, of course, when you think about building something much larger, then what that means is that you have dozens or hundreds of places in the code where you make use of implicit knowledge of how data is stored. And as a consequence, you can never again change the way you store this data, because this sort of implicit knowledge permeates your entire code. You might have to change hundreds of places in your code base if you decided that maybe this is not an appropriate way of storing the information. So you could, for example, think of maybe coming up with a triangulation class where the coordinates of your vertices are not given by actually storing x and y, but where you know, for example, that this is a uniform mesh, and you would want to compute these coordinates x and y by just knowing that let's say you want to access the 42nd vertex, you know that it's a 10 by 10 mesh, for example. So the 42nd vertex would be 4 over and 10 up, or something like this. So if you know delta x and delta y, you could compute the coordinates out of the number of the vertex. But you can never change this sort of thing, because you have made implicit use of these of knowledge of the data structures all throughout your code. So this is the reason why in object-oriented design we always try very, very hard not to expose the actual details of how we store data to the user. That we never make member variables public, but that instead we always want to have them private, and that we have to have ways where you can call a function of this class, triangulation for example, that gives you the coordinates of this vertex. Because if you do it this way, if you decide that you want to store it differently, then the only place where you have to change something is in the implementation of the function of triangulation, of this member function of triangulation, that actually returns the coordinates of a vertex. How it computes this is then up to this one place. All of the users of this information remain unchanged. So this is the first reason why this particular implementation is not a particularly good one, because there is a lack of encapsulation. The second reason why this is an unsuitable data structure is something that I would call, the second reason why this is not an appropriate design is something that I would call an unsuitable data structure. Namely, the way we store this in big arrays. So if you look at here these arrays vertices and the array cells, that is essentially a static way to do it. If you have one big array for a lot of elements, it becomes very difficult to insert new vertices, for example, or to insert new cells, or maybe to delete them. Now, this is fine if you don't expect your mesh to ever change. But let's say if you think, for example, of adaptive mesh refinement, your mesh changes all the time, right? You want to replace one cell by its 4 children, or if you have triangles, by its 3 children. Or if you have red and green refinement, then you also have to have a case where you store either 4 or 2 children for a triangle. Conversely, maybe you want to also coarsen cells. So you find that in certain areas your mesh is very fine, but the solution is smooth. So you don't need all of these cells, and you want to throw away certain cells, and you want to replace them by the mother cell. So in a case like this, you end up with data structures that are highly dynamic. You need to insert elements and you need to delete elements. And just a big array is about as unsuitable for this task than almost any other data structure. So we need to have something that is more dynamic, that allows us to insert things, that allows us to renumber things, and so on and so forth. The third reason why this is not good design is inefficiency. Because in reality, of course, a finite element mesh stores much more information than just the location of the vertices and how they go together to form cells. In reality, a cell has not just the indices of the vertices, but it also needs to store, for example, what are the neighbors. So a triangle has 3 neighbors, some of which may not exist if you're at a boundary, for example. So we need to be able to go from a cell to its neighbors. Then oftentimes what you will find is that finite element codes store something that we call a material ID or a material index, that you use this, for example, if you have, let's say, a body that you want to compute the deformation of as a result of external forces. If this body is composed of different parts, let's say of steel and wood or of steel and concrete, then you would want to represent this on a cell-by-cell level, where certain cells are marked as steel and certain cells are marked as concrete. So you would often do this through something that we call a material index, which is essentially just an integer which enumerates information about the material. The triangulation itself doesn't know what this material index means, but it is something that you will need when you assemble the bilinear form, and so it is something that we store in the triangulation. Likewise, we might want to have an index that is called subdomain ID or subdomain index. That would be something that you would use in parallel computations, where you say this cell is part of subdomain 5, which is stored, for example, in processor 5. Or maybe some processors store more than one subdomain. But so you somehow need to identify which cells belongs where. And then oftentimes people want to attach other kinds of data to their cells. So if you go, for example, to step 18, you will find that we want to attach, for example, the stress state of a cell. And so we need to be able to attach this sort of information to every cell. That is something that we call user data. That is something that users can do with whatever they want, and so we typically store it as a void pointer. Now, if you think about how you use cells, finite element codes almost always do everything by loops over all the cells. And so think, for example, what we would do if you were to assemble the bilinear form that corresponds to whatever problem you want to solve. So if you do this, you need to initialize the FA values. That requires the mapping. The mapping needs to know where the vertices are. So I definitely need to know on every cell the vertex indices, and I need to go from there to the coordinates. And maybe I do need to know the material index. But let's say I have a sequential program, so it's not going to access the subdomain index. And for the assembly of matrices, if you have continuous finite elements, you don't need to know the neighbors either. And maybe you don't need user data. So what you're going to do is, let's say you're sitting on the first cell. You're going to access this sort of information, the vertex indices, and maybe the material index. And then you move to the second cell, and you're going to access again the vertex indices and the material index. And then you're going to move to the third cell, and you're going to do the same thing. So if your mesh consists of an array of cells, then let me graphically visualize what this means to access these individual elements. So I have color-coded these here. So what you're going to do is you're going to access the vertex indices of the first cell. So the first cell in memory lasts from here to here. So I'm going to access this blue element in memory. And I'm going to access this purplish element. but I'm not going to access these other ones here in this particular loop. And then I move on to the next cell, and I'm going to access again the vertex indices, that's the blue memory location here, and the purplish memory location. And then I move on to the next cell, and I'm going to access the blue and the purplish. So what you see here is that we traverse memory in a way that is not particularly well suited to modern processors. Modern processors are always structured in such a way that they have caches. So everything that resides in main memory, when you access it more than once, it moves into the cache. But processors know that when you access one particular location in memory, that they should also try to read ahead in memory so that they can already load this sort of stuff into the cache so that they can be accessed much faster from the processor. So processors very much appreciate it if you can structure data in such a way that if you access one element, that you're going to access the next one as well, and then the next one, and the next one. But this is not at all how we structured our data structure here, right? So we're going to jump around. We're going to access this element, and this element, and this element, and this element, and they might all be several bytes or maybe several dozen bytes apart. And so what's going to happen is the processor sees that we access this memory location. It's already going to load this one into the cache. Well, but we don't need to load this element into the cache because at least in this particular loop, we will never access it. And so the important realization is that in no loop do we typically access all of these elements. We always access subsets of this. So what we should do is we should have not just one array of cells, but we should structure it in such a way that all of the vertices are in one big array, and all of the neighbor indices are in one big array, and all of the material indices are in one big array, because then we can traverse these individual arrays sequentially. And sometimes if we don't need to access, for example, the neighbor indices, then, well, this will be an array in memory that for this particular loop we just never touch. So we need to sort of reorganize these sort of things, and here's one of the ways you could approach this sort of problem. So to address the encapsulation problem is that we need to separate the interface from the data structure. And this goes a little bit in the direction of how we do this in deal.II. So you have this triangulation class, and it has these cell iterators, or active cell iterators if you want to. They act essentially like pointers to a cell, right? And there's a function begin and a function end that gives us a pointer to the first one of these cells and a pointer to the last one of these cells. And how we store that, again, is not all that important. But the point is that when you dereference one of these iterators, you get essentially, so this is a pointer to a cell. Well, cell has member functions called vertex index, neighbor index, material index, and so on and so forth. And they can give you the sort of information that you're looking for. So you don't need to know in which member variables this is stored. You just call these functions. Now, let me show you how these functions compute the sort of information that you want. So let us say, for example, that in this triangulation we have member variables, a list of cells. A list is a good data structure to insert and delete elements. Then we have a vector, for example, for this cell to vertex array. So each cell needs to store 3 indices. So what this vector is going to have, its length will be 3 times the number of cells. And then we have one big array with the location of the vertices. So this function vertex in the cell structure, so you can say cell arrow vertex, and then, for example, let's say you wanted to have the second of these vertices. So it's going to ask the triangulation. Okay, so it stores a pointer to the triangulation. Okay, it stores an index that represents which cell it is. So let's say if index is 4, then that's the 4th cell of the triangulation. So I can get the indices of the vertices that correspond to the cell by multiplying index by 3, because every cell stores 3 vertices, and adding to it the offset within this cell. That's going to be the index of the vertex that I'm accessing. And then I'm going to ask this tria arrow vertices, that's this array here, for the actual location. of this vertex. So that returns the coordinates of this scene. So you see how we have structured it in such a way that the cell-to-vertex array is one big array, and the vertices array is also one big array. And so if this is something that you need to access in a particular loop, you're going to go through it sequentially, through both of these arrays actually. This is how we do it with basically all of the data that we have in our triangulation classes. In reality, the data structures are actually a little bit more complicated. So instead of storing a list of cells here, today we think of a triangulation, at least for adaptively refined meshes, in a different way. So if you think, for example, of you start in the simplest case with one big square. If you refine it once, you get 4 child cells. They live on level 1. Level 1 means once refined from the coarsest cell. And we want to enumerate them as 1.0, 1.1, 1.2, and over here we would have 1.3. And we have refined 1.3 once more. So the child cells here live on level 2, and I enumerate them 2.0 to 2.3. I can represent this sort of mesh that comes out of this as something that we call a quad tree. Namely, we start with the mother cell. It lives on level 0, and there was only one cell on level 0. It has 4 children, and the cell 1.3 has 4 children again. We call this a quad tree for obvious reasons, because every node has either 0 or 4 children. In 3D, if you do the same thing, it would be called an octree, because every cell has either 0 or 8 children. We can generalize this a little bit. If you start out with multiple cells on the coarse mesh, for example, these 4 here, and if you refine this a number of times, so this is an elastoplastic benchmark that I have this from. You have shear zones here, for example. So in this case, you would have on the coarsest level 4 cells, 0.0 to 0.3. Each one of these would be refined. For example, some of these children might have children again, and so on and so forth. So I have multiple trees. Multiple trees obviously is a forest. So the data structure that we use for this is what we call a quad forest, or in 3D the equivalent would be an oct forest. And the way we store this actually is, instead of just having one list for all of the cells, we have a list for all of the cells on level 0. We have one list for all of the cells on level 1, and so on and so forth. That's sort of an implementation detail, but this is how we store data. Let's move on to other parts of the data structures that we have to represent. So in practice, we typically have in finite elements codes only one particular representation of a triangulation class. So there is really not much of a reason to have different triangulation classes, other than maybe for cases where you would have a triangulation class that would be completely unstructured, and you might have a different class, for example, for structured meshes, or let's say for meshes that are axi-parallel. Let's say the typical finite difference IJK mesh. In deal.II, we really have only one triangulation class, but we have, of course, many different finite elements. And again, we come back to object-oriented design, where you would represent these sort of things through an abstract base class or an interface class in multiple implementations. So in deal.II, we have one abstract base class that is called finite element. It would declare a certain number of functions, for example, DFs per vertex, DFs per edge, and so on and so forth, that are all abstract. That means the base class only declares that these sort of functions exist, but it doesn't have an implementation. And then we have multiple implementations of this. For example, Fé-Lagrange, I should have changed this name. Fé-Lagrange is really what we call FAQ in deal.II. But you might also have an implementation Fé-Raviat-Thomas or Fé-Nederlek, and all of these are implementations of this interface. So the finite element hierarchy would be a really good use case of object-oriented design, where you have an abstract base class and multiple implementations of this. Similarly, the same thing is true for quadrature objects. So you would have an abstract base class that's called, for example, quadrature. It would have abstract functions that are that return the qth quadrature point, and the Q's quadrature weight, and then you would have multiple implementations of this. For example, the group of Gauss quadrature formulas or the trapezoidal rule. And yet another example of the sort of design of one base class, multiple implementations, would be the mapping classes, where you could have, let's say, a linear mapping, a quadratic mapping, you could have a Cartesian mapping, you could have higher order continuous mappings, we call them C1 mappings, and so on and so forth. I've already talked about the FA values object. So FA values is an object that combines the reference cell, the shape functions, the mappings, and the quadrature. Because in practice, it turns out that we almost never need to access, for example, shape functions without mappings, mappings without shape functions and mappings without quadrature. We always access them at once. And so FA values is something that introduces an abstraction over these three that provides us exactly the sort of things that we need to access in user codes without having to deal with the three interfaces of finite element classes, mapping classes, and quadrature classes. So we introduced FA values because there are certain things that you need to compute on every cell, and certain things that you don't need to compute, that you can cache, that you can compute only once and then never again. So for example, if you go back to the example of the Laplace equation, the bilinear form that we need to implement to assemble the elements of the Laplace matrix looked like this, right? So it was the sum over cells, the sum over quadrature points, the inverse of the Jacobian evaluated at the Q's quadrature point, the gradient of the shape function I, and so on and so forth. And so if you do this, then you find, for example, that from cell to cell, certain terms change and certain don't. For example, the Jacobian matrix has to be recomputed on every cell, and of course it's inverse. But the gradients of the shape function on the reference cell, so there should be gradient hat here, they don't change. They're the same every time. So this is something that we should compute once at the very beginning, let's say on the first cell. This is something that we have to compute on every cell. Even here, one of the things that we find out is, for example, if one cell is just a translation of another cell, then this j to the minus 1 doesn't actually change. So we only really need to recompute it when it's necessary. So FA values does these sort of things. It computes once things that are immutable. Whenever we move to the next cell, it recomputes the variable parts. And then it analyzes whether this cell is, for example, a translation or a translation and a rotation. And in these cases, it doesn't recompute the Jacobian or the determinant because they are the same. So all of these sort of things happen inside FA values without user intervention. These are things that you don't have to worry about in your user code. So these are the things that have to do with finite elements. Out of time constraints, I'm not going to talk about a number of other things. So in linear algebra, for example, we have to talk about how to represent matrices and so on and so forth. In matrices, we typically represent through a format that is called compressed sparse row. The term here is not correct. Compressed sparse row is what it should be. You can find these on the slides that I'm going to post with these online lectures. So there's a few slides on how to store matrices, and then there's a few more slides on, for example, linear solvers, and so on and so forth. So with this, let's move away from the design of data structures, and in the next lecture I'll come back to other things that have to do with writing code, namely documentation.